Hello everyone, welcome to this second session of the Electronic Design Laboratory, and today's very brief discussion will be on data sheets and packaging information for different electronic parts. So as you become more and more experienced of an engineer, you will delve into more and more difficult complex projects. It will very rarely happen that all the parts, or rather all the possible hardware parts that you will work with for the project will be known to you. So that never happens. For different applications, different projects, in fact, the best example possibly is the 4G signal monitor, which we had discussed in the previous session. You came across at least 2-3 new components which you did not know. So almost every new project which you do will cause you to encounter some new component, some part which you have not come across before. So, and it is also not proper to expect that an engineer will have the full idea of each and every part that is available under the sun. So therefore, today's electronic hardware market has so many different products to cater to even a single application. It is very important that those parts, in order to be more commercially viable, they be accompanied with some kind of a support system, and that support system will tell the designer or the engineer how to use the part. So therefore, that support system is called as a data sheet. So a data sheet of any electronic hardware product is a comprehensive document that is released by the company itself who manufactures the product. Obviously, only the person who makes them can release such a document. So generally, data sheet contains a lot of information, including the characteristics of that device or component, what is inside, if it is a complex device, what is its internal architecture, some examples on how to use that device for some particular application, and more. So a good data sheets or a good data sheet of any product will tell the user what are the good ways to use the product and what are the ways you should not use the product. But at the same time, since the design of that chip or that part is a commercial secret for the company, they will generally not reveal too many secrets behind how that exact chip or part has been designed. So a good data sheet will tell you how to use it without bothering too much about what went on into designing it. Now, it is expected that as an electronic designer, you should spend considerable amount of time to go through the data sheet of that part, which will save your time, efforts, probably money, because if you do some wrong experiment and the design goes wrong, you will have to refabricate your design. So many data sheets, especially for parts which are very complex and big, they are very detailed. Data sheets can go as big as 400 pages. So therefore, but most data sheets you will come across are not 400 pages. They may be something as low as 10 pages, or it can even be 2 pages. Many are of the order of 15 to 20 pages. So the question now is that as you read more and more data sheets for a part, you should develop the skill of knowing what to look for. Now, it is not possible to read 20-30 pages for every part that you come across in your life. So you must quickly develop the skill of hunting for information that is of interest to you, that is inside the data sheet. So then again, many companies are not very good in that way. They give data sheets which are really brief. They do not give too much of information, maybe just the bare minimum. So in such cases, if you are not very confident, you should look for other parts to do the same task, or you should learn to read between the lines and develop confidence. Now, most good datasheets uh, are organized into these about 7 different sections. The first is the overview, which is like an abstract, which tells you a bird's eye view of what the datasheet or the part is all about. So you should read that first. If it is of interest to you, then go ahead. Otherwise, just throw it away. After overview comes key features. Key features is again something that you could look for if you don't want to read the abstract. So the key features are generally a pointwise description of some of the most important electrical parameters, which is the selling point of the part. For example, if a manufacturer is selling an op-amp IC, then the manufacturer, the points which the manufacturer may give as a key feature will include gain, open loop gain, bandwidth, slew rate, so on and so forth. Because these are the points which will help him sell his product. Then comes a functional diagram. Many manufacturers give either a circuit diagram or a block diagram of what is exactly inside the part or the chip or whatever it may be. So this might be useful if you are interested in what is inside. Then comes some things which are very important. The characteristics of that part. Means how that part behaves in a circuit. The first section of characteristic, which is most important, is the absolute maximum ratings. That means the maximum voltage, the maximum current, the maximum power, for example, the maximum temperature, which that device can withstand without breaking down. So these are nothing but safety information that the designer should keep this in mind and use the part in safe operating conditions. Then comes the electrical characteristics, AC, DC, whatever is applicable. For example, gain, bandwidth, current gain, slew rate, then power consumption, bias current. These are the examples of any particular analog IC, for example. Then comes characteristic plots. Some plots or graphs which will describe the functioning of that particular part in good detail. Say, for example, if it is a transistor, then it's IV plots for the base emitter junction, the collector base junction, so on and so forth. You can even have frequency response plots, Smith charts in some cases, which shows how the impedance of a particular device is matched. So these can be different things. It can also show you the spectrum of a wave that comes out of an IC. So after that comes the functional information. That means how different or how the different parts of the circuit they work, and that this may be of interest to you if you are deciding to consider this IC seriously. And after that is the application information. How can you use this particular part for a few selected number of applications? This is just to give a helping hand to the designer, help him get started. And finally, last but not the least, comes the package outline drawings. That means, as you know, every different part or every different chip or some component is packaged in some way. Now, how or what are these packages, what are their sizes, what are the dimensions? These are very important information when you are going to use this IC or this part as part of a printed circuit board layout. You will know how much space it consumes, you will know how many pins it has, this kind of information. So having said that, we've completed what a datasheet involves. Now let us look more about this thing called as packaging. Any electronic component, starting from the simplest of electronic components such as R, L and C, right up to the most complex electronic components you will come across, which includes things like microprocessors. Every electronic part under the sun comes in the form of a package. So this is something which you have seen many times in your labs. These are the diagrams of resistors, capacitors and inductors, which are easily used on the breadboard. But what you see over here is these have two pins which are normally inserted into the breadboard, and these kind of packages are called as through-hole packages, and we define a quantity called as pitch, or the smallest distance between two pins. So the pitch for the resistor and inductor can be roughly about 7 to 7.5 millimeters because they are little longer. The capacitors, since they are smaller, the pitch is 2.54 millimeters. So interestingly, 2.54 millimeters is also the distance between two neighboring holes on a breadboard. So the capacitors in particular are designed to be inserted on the breadboard as it is. So if you notice, the last, this big thing is also an inductor, but of a large value. It's so big because it needs a large number of coils and wiring inside it. Now, although we have used these through-hole packages, one small drawback of them is that when you are mounting these on a PCB, you need two layers. One side for the component to mount and the one side for soldering. Let me give you an example. I am now holding one example PCB. In fact, if you have a good memory, you will know that this is the photo of the PCB, or the photo of this PCB we have seen in the previous class, the previous lab session. Now this PCB has multiple points for soldering resistance or resistors. So for example, over here you can see a lot of outlines and holes made for resistors. What I am now holding is an example of a through-hole resistor. As you can see, this is something you have used very commonly in your circuit labs. So now let us see how to mount this resistor on the PCB. As you can see, I have now mounted one resistor on the PCB. So this side where you can see the resistance body is called as the component side. Whereas if you notice, the other two legs are coming out from the other side. So therefore, while the component sits on top, the soldering has to be done on the other side. So this is one drawback of using through-hole packaging components. That is, you will need two layers. So therefore, you will need to drill holes. But they are very easy to use, and drilling holes these days is no longer a big concern. We have automated machinery for that. Now, such components can be used if PCB size is not a concern. That means you have ample amount of space for the components to be mounted. Or, now the second point is very important. If you are using signals on the board whose maximum, or the signals in your circuit board whose frequency generally should not exceed 20 or 30 megahertz. Why? It is because at very high frequencies, even the long legs of these components start acting in a parasitic manner. These legs, which we very conveniently assume as good conductors, will be used or will exhibit tendencies of an inductor. So therefore, what you will have is not just resistance, you will have a resistance plus a j omega L component which will add to the parasitic. And as the frequency increases, the parasitic inductance effect will also increase. So therefore, if you are using components for high frequency circuits, say for example microwave circuits, or RF circuits. In that case, it is a very good idea to go for resistors, capacitors, etc., whose packaging does not have any leads. So these kind of devices are called as surface mount devices. Now, good part is that they are much smaller as compared to your through hole components. So therefore, they take a lot less size, and they need only one layer for soldering as well as mounting. So wherever you are mounting, whichever side of the PCB you are mounting the component, the very same layer has to be used for soldering. So for example, this diagram shows you two resistors which are surface mount. If you can see over here, the ends are metallized so that they can be soldered along with the pad on the same layer in the PCB. Now, you can see that there are two different sizes. One is 0603, the other is 1206. Now, these are not the values, but these indicate sizes. So, 1206 stands for 0.012 inch cross 0.006 inch. 0603 stands for 0.006 inch by 0.003 inch, or 120. Oh, I'm sorry, this is a small mistake. It's 120 mils by 60 mils. So where 1 mil stands for, where 1 mil is 1 by 1,000th of an inch. So therefore, it should be 0.12 inch by 0.06 inch, not the extra zero. I'm sorry, there has been a small error. For example, the 0603 also stands for 0.06 inch by 0.03 inch. Now I'm showing you some examples of commonly used input devices. The first three, what you can see, are through hole. The first two are push button switches. One is a 2-terminal switch, the second is a 4-terminal switch, and the third is a single pole double throw switch, which is also called as a slider. This is a through hole. Then you have something called as a thumb wheel switch, which can give output in the form of a multiple n-bit digital value. Then you have other forms of surface mount push buttons, which are called as dome switches. Now, another example is something called as a dual inline switch, which are double pole double throw switches. Output devices include LEDs. The first two are through hole, whereas the third is an example of a 1206 SMD LED, which is a surface mount device. So once again, I repeat, 1206 stands for the long side being 0.12 inch and the short side being 0.06 inch. You also have different other kinds of output devices for LEDs. Now let us go to chip packages. The first, this is something you have commonly used in your circuit labs. This packaging has a name. It is called dual inline or DIL. As you can see, it's a through hole package because it can be mounted on the breadboard. The pitch, that is the distance between two consecutive pins, is the same as that of the breadboard, which is 2.54 millimeters. But if you are using this DIL chip to solder, you will need a base for it, because if you want to replace this IC at a later point of time, then you will need a base. Directly soldering will cause a lot of difficulty for replacement. Now, the next version of, or the next smaller size of this package is a surface mount package, which is called as a small outline IC or an SOIC. Its pitch is exactly half of the DIL package, as you can see, there are pads, surface mount pads, there are no holes. So you cannot mount this on the breadboard. So the next smaller version is called as a TSOP, thin shrink small outline package, whose pitch is again almost roughly half of that of the SOIC. Now all of these things are hand solderable, although you will need some amount of expertise for the SOIC and TSOP packages. So if you develop good amount of expertise in soldering, you could do this yourself. I have also listed some applications of each of these packages where they are commonly used. Now let's go to more complex ICs. Until now, the ICs that we saw, the chips that we saw, they have pins on only two sides. Now in this particular slide, I am showing you something which has chips on all four sides. So rather they are square in geometry. So the first one is called a plastic lead chip carrier, or PLCC. So these are throughhole components because they need a base. Now what happens is, if you see these pins, they are in the form of a closed ring. If you notice this very carefully, this metallic pad is coming out and then it is bending inside. So therefore you need a mounting base, which I have shown here, and then this will be inserted on the PCB. Its pitch is 1.27 millimeter of the device. So this can be hand solderable. Then comes the second one, which is called as TQFP, or a thin quad flat package. Now these ones can be very difficult to solder. Their pitches can change anywhere from 0.4 to 0.8 millimeters, and most microcontrollers, FPGAs, many of them use this kind of a packaging. And then the third one is called quad flat but no lead, QFN. It is similar to QFP, the second one, but there are no leads. That means the pins which you can see coming out, they are not here. They merely have a metallization on the surface package, and that is all you have. The reason why they do this is because most QFN packages, whose photo top and bottom view you can see, they give very less amount of additional metal outside the package body, is because these kind of chips are used for high frequency applications. So to keep the parasitic components, parasitic inductance, capacitance, etc. at a bare minimum, we cannot, I mean, the manufacturers prefer that not to give any kind of leads. So therefore, this is one of the most difficult ones to solder. It's doable by hand, but you need immense amount of expertise to do this. This is probably one of the only packages which I myself cannot solder. I need help to do this. All the other packages I can solder. So this should tell you a little bit about this IC, and the pitch is also quite small, roughly about 0.4 or 0.5 millimeters. So this makes your life a lot more difficult. So I would suggest, if you are learning how to solder, don't start from QFN. Start from something easier. So with this, we come to the end of this brief discussion. Thank you.